And so again, if the weak solution agrees with the smooth solution times 0, then it agrees with the solution until the first self-intersection, the first collision. This is kind of striking because in general, there's just no uniqueness at all for weak solutions. I gave you examples of non-uniqueness. One example is these things who collide and then either vanish or don't vanish, or else they can simultaneously vanish here and appear someplace else and move away from each other. Those are all perfect weak solutions. Another would be I could have things who hit transversely, and they can either again pass through each other or change topology and connect and continue from there. And so all these things can be constructed rigorously with the existence theorem I've just quoted. So as soon as there's a collision, I have two choices: either the two things pass through each other, or do they not reconnect? And so one can never have uniqueness in the presence of a self-intersection. Okay, and so this is a weak uniqueness theorem. In fact, it proves more than that. So as we'll see, it proves that a kind of stability, and so it shows that as I've written down below, a weak binormal curvature flow who starts near a smooth flow remains close for some time. And what I hope to show you is I have movies, simulations illustrating this. Unfortunately, the simulations are in a format that I'm no longer able to play. There's this AVI format, and my devices used to be able to run it, and now they can't. And so if I can get that running, I'll show it to you later. Those are interesting. Okay, as I remarked a moment ago, self-intersection always lead to non-uniqueness. And uniqueness can fail if I drop. So again, one of the main conditions in the definition of weak solution is that so this V sub t here, this is the, if you like, the generalized arc length at time t. This generalized arc length at time t is bounded by the arc length at time 0. And that prevents pairs of vortices, vortex rings being born out of a vacuum and moving away from each other. If I drop that condition, I can always have non-uniqueness at any time. Okay, and so so this is the theorem, and I would like to discuss its proof today. And okay, so here I've recalled the definition of the class of things we're working on. So V sub t is a measure on R3 cross S2, and it satisfies these properties. Let's slide this over a little bit. Okay, thank you. So, okay, and so the main property is the second one. So this is the thing that in some way looks like the old equations. Okay, and so my situation is I have this V sub t, this sort of abstract object, this family of measures parameterized by t, some kind of generalized surface, who has these properties. And so it's a solution in some sense, in the weakness of the binormal curvature flow, satisfies the right balance laws. I also have a smooth solution, and I want to estimate the difference between the smooth solution and the weak solution somehow. All I can do, there's only one thing I can do, and it is this. All I know about the weak solution is how it acts on test functions on vector fields. And so really the only thing I can do is take the smooth function, the smooth solution, little gamma, build a vector field out of it, give it to this identity here, and hope that I get out some useful information. That's really the only possible argument. Okay, and so what I want to do is I'd like to build a vector field. I'd like to build a vector field out of the smooth curve little gamma that tells me something about how far the smooth curve is from the rough curve. And let me tell you how I do that. So the plan is I want to build a vector field phi out of the smooth solution it should control, I would like it to. Some kind of distance from gamma to V And I hope I can then use the definition of weak solution to compute how it changes in time. And hope for the best. Okay, and let me remark, the vector field I'm going to build will depend on both x and t. Here I assumed that phi is a function of x alone. And so if phi depends on both x and t, well then on the right-hand side, I'll get an additional term involving d phi dt log c times v sub t. I'll get that. That's no mystery. It's usually practical. Okay, and so when I use this, I'll have an additional term on the right-hand side involving time derivatives. Okay, so let me tell you how to build the vector field. Let me draw a picture as follows. And so I have a smooth curve. So let me imagine t is fixed, and I'll tell you how to do this at a fixed t. Well, so first of all, actually, let's fix r positive such that for all 0. You see, I have this smooth curve and it has no self-intersections. And so, so what this means is that I can put a tube around the curve, a tube of positive radius, such that at every point in the curve, there's at every point in the tube, there's a unique closest point on the curve. If, let's say, let's let gamma sub t be the image of the smooth curve. Okay, so little gamma is the parameterization, capital gamma is this image. So if the distance of x to gamma sub t is less than r, then there's a unique closest point. In gamma sub t to x. The emphasis being on unique, gamma sub t is a convex set. There's always a closest point. Okay, and so this is some kind of security radius, if you like. Okay, and so then everything I'll do will be in this security radius. And so for, and so I'll always assume I may not always, I may forget to mention this. X in the X such that the distance of X to gamma T is less than R. Okay, so in this tube, in a small tube. Okay, and then for such X, let's let P of X be the closest point. I should probably call it P sub T, but so here I'm thinking of T as being frozen for now. And what do I want? And so here's a picture. I have a smooth curve, and I have this security radius. I have a tube around it. And I'm looking at a point in the tube. And I wanted to find a vector field there. And so the natural thing to do is, well, okay, well, so what I'm going to do, natural not, is I'll look at the closest one on the curve, which may be here. I'll look at the unit tangent there. And out here, the vector field to find will be parallel to the unit tangent. And so what I want is for it to exactly equal the unit tangent when I'm on the curve. And then as I move away, it'll decay at some rate. So let's define, so let's let x gamma r be, so I look at the t. Oh, okay, let me suppress the t variable for convenience. The tangent at p of x times some function f of d of x. And so here, the t is the so I have a direction of the tangent given by the parameterization. So this is, I find the value of s at a point, say, y in gamma. So this is d little gamma, ds at the right value of s. And then d of x is the distance from x to gamma, which is exactly x minus p of x, because p of x is the unique closest point. Okay, and so what's f? And f is a function such that, let's see, I want f is 0. F of f of sigma is 0 if sigma is bigger than r. And so so outside this tube, my vector field will vanish. F is between 0 and 1, and f is like let's say for here. So f and f is smooth. Okay, and so then f looks like this. Near at 0, it's equal to 1, and then it decreases from 1 quadratically, and then okay, it does something smooth and ends up being convex toward. Okay, and so then my vector field at a point here, it will look like the tangent vector at the closest point on the curve, but it gets shorter as I move away from the curve. Okay, and so then consider well, let's see, maybe I'll go down and see. I've written some stuff here. Okay, let's to go through this more slowly. Let's write it by hand. So now, given gamma as above, and varifold v, I want to consider the following quantity. Okay. Okay, so the situation here is there a question? Should one of the bonds on F? Oh, sorry. Yeah, there was a question. And so here, I wanted F to be, so this was a little c and this is a big C. I guess the lower bound is unnecessary because F is smooth. And so it can't decay from its maximum more quickly than quadratically. But okay, so that's so consider this, and so this is the thing I'm going to use to track the distance between between the smooth curve gamma and the rough curve capital V. So we think of capital V as being rough curve. Okay, and so then right, and so here's my claim. So let's again look at the picture. And so what I want to do, I'd like to imagine that within this tube, well, so first of all, outside the tube, this integrand is equal to 1, because outside the tube, this capital X vanishes. And so if the whole varifold lives outside here someplace, then I would integrate 1 over the variable over the, say, the generalized arginate of the variable, and that will just give me the length of the variable. And so that will tell me that the variable, the rough curve, is far from the smooth curve. So let's imagine then that the rough curve is within the tube mostly, and so then we can picture it as being, I don't know what it looks like. Well, it's rough, it's dangerous, it's red, and so it does. Who knows what it does? And so let's look at the, so let's say, so let's consider a point here, and there's a, so there's a, okay, it's got a spatial location X, and there's a tangent vector C. And so let's say, X C is in the support of V, and X X is within the tube. What does this integrand mean? 1 minus capital X gamma R. Okay, and so what I want this to do, I'd like it to tell me something about the distance from X to the smooth curve little gamma, and I'd also like to tell me something about the deviation of the tangent vector C to the rough curve from the tangent vector capital T to the smooth curve. Okay, let's see if it does that. And so by definition, this is 1 minus this function of the distance times the tangent vector of the smooth curve, the dot product with the tangent vector of the rough curve. And of course, I'll do what I always do. I'll add and subtract, and I'll do what analysts always do, what everyone always does. Times, I feel like I have something backwards here, but let's see if I do. I do have something backwards. Good. Okay, and so then the first term, if you look at it, so T and C are both unit vectors. this is a trick that's used all the time in certain areas of math. And so the first term is really t minus c, the Euclidean norm squared times 1/2. Because what is that? That's t squared plus c squared, and okay, those numbers are both 1 because they're unit vectors, minus 2t dot c. So I get 2 minus 2 t dot c divided by 2. I get this. So since t and c are 1. Okay, and so this really tells me the square of the difference between the tangent of the smooth curve and the rough curve. And then if I look at the second term, well, 1 minus f dot c is like, well, what it was like basically distance squared of x times t dot c. Okay, that looks too ugly. And so this is comparable. It's bounded above and below by the distance squared between the point and the curve. And so that's a positive quantity. Okay, so then let's consider what happens here. So there should be two cases. If t dot c is bigger than 1/2, so if the rough curve and the smooth curve are pointing in kind of the same directions, then I want to drive that up here. Then this is bounded. Then this quantity, this integrand, is bigger than is bigger than something that measures the distance squared of the point from the curve and the distance squared of the tangent from the tangent. Okay, that's good. I like that. If t dot c is less than 1/2, then the whole thing is at least, say, I think we can say the whole thing. Well, yeah, so then if I look at the top, I have 1 minus something who's less than 1/2. And again, it's bigger than a constant times t minus c squared plus x minus p of x squared in the tube, because in the tube, t minus c squared is always bounded by 2 or by 4, something like that. And x minus p of x is always bounded by r squared. Okay, and so in the tube. Okay, so then as long as, so outside the tube, I don't care what happens. And inside the tube, this integrand really controls so if I then imagine integrating with respect to v, so integrating over the length of the rough curve, so what am I getting? I'm getting the integral of the distance squared from the smooth curve, and then the integral of the difference squared of the tangent vectors of the square distance of the tangent to the rough curve from that of the smooth curve. And so if you like, it's kind of it's like a H1 norm, right? H1 norm has position squared plus derivative squared. Here it's a geometric H1 norm of the rough curve to the smooth curve. That's kind of interesting. So the above quantity, 1 minus x gamma r is like a geometric well, it is, let's say, is bigger than this. Over, and so this is the tube cross S2 plus the varifold measure of the tube complement cross S2. Okay, that's regrouped. And so, and again, this is geometric eternal. Okay, good. And so, so what was our plan? Our plan was to build a vector field out of the smooth curve gamma. And now, and we've done this. I didn't tell you where this comes from. We did this, and we've shown that indeed it controls kind of a distance from little gamma to capital gamma. And so in particular, if the integral over, if this integral vanishes, then the support of the varifold is contained in the image of, is contained in the smooth curve gamma. And moreover, at every point in support, the tangent of the varifold, the tangent of the rough curve is tangent of the smooth curve gamma. And okay, so here I've stated some of this. Okay, so there's a lemma which says that, and here's where we rely on the assumption that V is closed, that V, when it acts on gradient vector fields in the natural way, it yields 0. So V is closed in that sense. Okay, and so first time is that if the, so here I gave this a name, what did I call it? Relative excess. That's exactly what we wrote down before, except I called it little t instead of capital T. And I wrote an explicit function f with the properties I asked for. Okay, and so the point is that if this quantity, if this excess is equal to 0, then as we just said, the this integral of distance squared is 0. So these properties we just summarized, I don't remember myself, imply in fact that the varifold is a multiple of the measure corresponding to integration over the smooth curve gamma. Okay, and so and that uses a bit of geometric measure theory machinery, but the idea should be believable, at least given what we said so far. Okay, and so what I want to do now is the final step. I'd like to control. I'd like to use the definition of weak solution to control the growth in time. So let me emphasize the definitions of these different features. I just used this one. That was for the lemma I stated, which says that if the excess is 0, then the rough curve is a multiple of the smooth curve. I now want to use these two. Okay, and so so now let's prove the, I can't remember if it's a proposition theorem. So it should be a theorem. So this is the weak, strong uniqueness and indeed controlled. So what we'll show is that if this excess is small at time 0, we'll show that if it vanishes initially, then it vanishes in this time interval as long as the smooth curve has no self-intersections. And the same proof will imply that if it's small initially, then it remains small, I mean, on the same scale. We can control the rate at which it grows. And so this says that if the rough curve is initially close to the smooth curve, in the sense of this relative, whatever it is being small, then it remains close in the sense that that quantity stays on the same scale. If it's initially epsilon, then at later times it'll be some constant, e to the ct times epsilon first. Okay, and so that's the theorem. And let's define, so we have a smooth solution gamma and a weak solution V. And so we define X x of, okay, I look at the solution at time t, and I have this security radius, which is valid for every time in the time interval I'm considering, and I dot that at x as above, and I let, say, f at time t be, well, this quantity we've just been considering. And then I integrate against this v sub t, who represents the rough curve at time t. Okay, so what I can do with my definition of weak solution is I can definitely control the interval of, I can control the, if I didn't have this thing here, I can differentiate that because I control how, so that's exactly what the weak solution tells me is if I let the variable act on a vector field, which I have here, then I can compute the change of that in time. I don't know how to compute the ddt of the whole v sub t, but I have, let me also define g of t. Oops. Is, okay, so I'll use my third assumption. And so the third assumption is that at every time, so if I look at the first thing, the integral of v of t over r squared, so that's just this. That's this here. And at every time it's bounded by this thing, which is the arc length at time 0. So let's just replace this by and so then g of t is bigger than f of t for all t by this third property here of a weak solution. And then g of t is something you can differentiate because the first term is now constant. Okay, and I can use the definition of weak solution to differentiate g of t. And so okay, so let's do this. So I'll have a, as we said, I'll have a term where I differentiate now I have a time-dependent vector field, and then I'll have a term where I use the definition of weak solution, and I forget the sign. I hope the signs are right here, and I'm a bit worried. Okay, it's this minus gradient curl of x c tensor c. And I integrate this whole thing okay, and at this point I've used everything I know about my weak solution. And I don't know any more about it. I don't know, for example, where is this measure supported? I mean, it's an R3. Well, I don't know anything. And so, and I want to prove a bound for this. I want to bound the rate of growth of this quantity who measures the distance of gamma from the rough curve from the smooth curve. And so all I can do is, and so here's the key fact is that, so I don't know what C is. I don't know, C is the 10, I don't know what X is. I think what's in the tube, it may as well be in the tube. And I don't know what C is. Like C could be, is the tangent of the rough curve, it could be anything. And so what I have to prove is some inequality for this integrand that's valid everywhere for every X and for every C. And so here's the claim. And so the claim is, there exists some K. All these constants depend on R, for example, on the security rates. So you can see that you can see that in for example, in the explicit formula I had for R in the previous slide, that when I differentiate anything, I'll get things sort of down to 1 over R. But there's this K such that this thing, and let me check down here and get the signs right. I feel like I had a sign wrong, but okay. So the claim is, and well, there's no way of knowing without doing the whole calculation. So there's this case such that this thing, this integrand, minus dx dt dot c minus plus gradient curl of x tensor c dot c, that this is less than, well, I want to be less than this integrand. If I can bound the rate of growth of, if I can bound the integrand in dg dt by the integrand in f, then I can bound dg dt by f, and which in turn is bounded by g. So then I have an inequality of the form dg dt is less than or equal to constant times g, and then I can prove things. So so I need this to be bounded by a constant. One minus x dot c. And what I've done here, I should have, for convenience, I stopped writing x sub gamma comma r, but I should have kept writing it right, because remember, x is built out of this vector field, out of the smooth curve little gamma, and little gamma solves a PDE, and that's all I know about it. But x is built in a model, so x is gamma r, and gamma depends on t. And here is x, and here is x. Right, and so here's the claim. So this is what we just got to do, like move through more slowly. And so we define G as above. It's bigger than F, which measures the distance of the rough curve to the smooth curve. And the claim is that G is elliptic, and we can bound its derivative as done here. And so this reduces, I guess I've done this, this reduces to a pointwise inequality for all x and for all c involving this thing here. And so, okay, so what do we do? Like, if I look at capital X, it involves, so it's built around the smooth curve gamma, and gamma solves PD. So when I differentiate it, you know, the for example, the tangent vector to the curve appears in the definition of capital X. So I'll get derivatives of the tangent vector, which is, you know, gamma st. That'll involve, when you use the PD, you get third derivatives of the curve gamma. Anyway, so you do a calculation. And I'll spare you the details, which would take not that much time, but that'll take some time to do. Okay, so here's the notation. What's the notation? Okay, so the main notation is x perp is the vector connecting the point x to the nearest point on the curve. It's the vector of, from the curve to the point x. Okay, d is the distance, t is the tangent at the projected point. And these things, these kappa n refer to the projected point. Xi is the tangent vector, and then xi perp is the so xi is the tangent to the rough curve, and xi perp is the part of that vector who is orthogonal to the tangent vector to the smooth curve. Okay, and so the stuff that and so remember we want to bound all this thing by this. And as we've seen, this controls basically distance squared. This already controls distance squared plus xi perp squared. And so what I'd like to do is compute this, get a horrible mess, and then bound everything by terms that involve either distance squared, d squared, or xi perp squared. And if I can do that, then I'll be in pretty good shape. So here's the horrible mess. Here's what you get if you just compute that expression, expand everything, etc. And so let's look at it. And so the terms fall into two categories. I guess the first ones up to here are a quadratic in xi. And so these will come from the term involving the gradient of the curl of the tensor with xi tensor xi. So those are the quadratic terms. And then these terms are linear in xi, looks like. And so what we'll do is we'll just stare at these and we'll see that everything works out. And so a lot of them are small anyway. Like if I look at the first term, I have a x perp. It's already, so again, I'm trying to bound things by either x perp squared or xi perp squared. And so that's okay. And I go through it in that way. You know, kappa is the curvature of the smooth curve. I'm just assuming that's bounded. That's a bounded constant in my time level. And so on and so on. And so then, right. So here's what we get if we just do the easy things. The first term is bounded by x perp squared. The second term, okay, well, here's a tau t cross xi. T is tangent. This is going to pick up the orthogonal part of xi, so xi perp, and then xi dot x perp is the dot product of xi with the vector which is orthogonal to the tangent, and so that'll also be xi perp. So here I have again x squared, xi perp squared, etc. And so okay, most terms are already small, are already bounded by things that are quadratic in terms of x perp and xi perp, but some of them aren't. And so I have these four troublesome terms. But also, I haven't yet used the PDE. I haven't used the fact that little gamma is a smooth solution of the binormal curvature flow. And so what we do then is we can combine those four terms. And so here's a term. You see, in each of these things here, I have a piece who's quadratic in xi. I have a xi here and a xi there. And I have a piece of linear in xi. And so that involves this xi multiplied by these functions who don't contain any xi. Okay, and so this is a piece coming from the xi tangent xi part and a piece coming from the time derivative part. And the other term has the same structure. And okay, we're out of time, but we may or may not stare at this for a couple of minutes at the beginning of the next lecture. But what happens is by this sort of miraculous, there are these, say, striking cancellations where the structure of the test vector field and the equation, the binormal curvature flow equation is satisfied by the smooth curve little gamma out of which we built the vector field capital X collaborate, they collude in order to give us these quadratic quantities we need to then bound all of this by the integrand in F. And so that's the idea of this weak, okay, that's the idea of weak strong union instability, and with that we'll finish our definition, our discussion of the weak solutions of the binormal curvature flow, and we'll go back to the Euler equation, and that's the plan for next week. Okay, that's it for now. Any questions? I'll stick around for a little while if you have any questions. And but yeah, so while I stick around, I'm going to stare at this and see if I can remember why the red terms are small. So the first term, okay, so there's already X perp here. I'm just entertaining myself by staring at this. This has an X perp. And then C minus tau. Okay, so this vector, I guess C minus tau is basically controlled by C perp. Right? If I have a that's true, and so the C minus tau minus the tangent becomes a C perp. And similarly over here, I have a what is this? Because of the dot product with T and the cross product, I could rewrite this as up to a sine T cross C dot product with something. And so that's going to involve a C perp here. And then I guess I claim that this looks like C perp plus X perp. And I don't know if I can see that right now. Rho. What is rho? Oh, rho is, I didn't even say what this is. Anyway, so since I forgot to say what rho is, I can't, we may not be able to see why this is small. But anyway, the structures, we get these remarkable cancellations. And a question which I personally am very interested in, and which maybe no one else is, or not many people, is so one can do all this. One can at least write down the corresponding definition of weak solution to the binormal curvature flow in arbitrary dimensions, and we expect. So there should be an analog of this weak strong uniqueness theorem in arbitrary dimensions. You can write down everything. What should be what's the natural generalization of the, of the flow of the PD for little gamma, the smooth thing, of the definition of weak solution that has natural extension. And then one can write down the corresponding definition of the test vector field. It's got to be true. Well, okay, it doesn't have to be true, but I sort of believe it should be true that some computation like this will hold. But if you try to do it, it's a huge mess. I mean, this was a minor. I mean, this is so this is from a paper with myself and Smets, and there the calculation I made is like just 3 or 4 pages of calculus. It's not that big a deal. Again, it's just it's undergraduate level calculus. We're just differentiating cross products and stuff like that. But if you want to do this in higher dimensions, well, for one thing, instead of, so here we can use the language of vector calculus. And if I want to do it in general, I have to use either geometric measure theory or differential geometry. I have to use the language of forms or currents or something like that. And so the analog of the vector field, in R3, I can identify a vector field with a 2 form by duality. And so in every dimension, you can write the weak solutions as acting on 2 forms. what happens. They act on two forms, but then as soon as you're in more than 3 dimensions, a two form is more complicated object. So a two form has, it looks like it has indices, omega, say eta ij, where ij go from 0 up to the dimension. And so I believe that this got to be true, but I've never had the block of time it would need to do to sort those. And it's not just vector calculus. You have to do it in a smart way. But that's a question that, for me at least, is an interesting question. Okay. Anyway, I'm just talking. And if any of you have any questions, I'd be happy to discuss them.